Welcome back to the second lecture on bioelectrochemistry. In the first lecture, we kind of started the course, and today we will be outlining all the points what we'll be dealing in next 4 classes, which includes this class also. And apart from it, we will talk about some of the very basic concepts. So, let us start today's lecture. So, this is our lecture 2. Out of 20. Okay. One aspect which I wish to highlight is when we talk about electrochemistry, there are 2 ways you can look at it: a chemical reaction leading to generation of electricity, or electricity driving a chemical reaction. In other words, when you apply electricity to break down a compound, which is electrocatalysis, so you are using electrical energy to break a compound. Similarly, when there is a chemical reaction taking place where there are electron transfer taking place, so you are harvesting electricity from it, and both these are fairly common if you look around. Say for example, when we go to metal purification plants where from different kind of ores metals are being purified, there are a lot of electrocatalysis is being used. Similarly, when we talk about a battery or some other fuel cell or some energy harvesting system, that is where we see we harvest the energy which is generated or the electrons which are being generated during chemical reaction. So, in other words, when we talk about electrochemistry, these 2 aspects needed to be kept in mind, and these 2 are dealt kind of in a separate way. So, one is where electrical energy driving chemical reaction. Similarly, electrical energy harvested from chemical reaction, harvested from chemical reaction. In other words, you are funneling out the electron transferred between chemical species due to potential difference between them. If you remember in the last class, we talked about why an electron should flow from a species A to species B or point A to point B. The flow takes place because of the potential difference, or in other words, the energy function of that particular material. So, we can always have a scale which can tell you whether the electron from point A will flow to point B or not, and how much energy we needed for a reverse reaction to take place to raise an electron from a lower potential to higher potential, which is an energy intensive process. So, keep these two aspects very clearly in mind, because both have their applications in the industry, and this is one industry, electrochemistry is one industry which is part and parcel of our day to day life. At every quarter, we have used these electrochemical techniques time and again, time and again, and time and again. So, that is why it is one of the industrially very relevant subject and is being used from energy sector to electroplating to electroanalytical as a tool, as a detection tool, as a sensor, as a biosensor, as diagnostics, and that is why a basic understanding, a very fundamental understanding of the subject is exceptionally critical, and that is why I will be going slowly in these small capsule. My desire will be that once you finish this course, you should be able to kind of see the power or how empowered you are to think of a problem depending on which aspect you are dealing with, and how you can use these powerful tools to resolve them. And especially it is even more important to realize much of these electrochemical techniques are not very costly. They are doable, they are not a very high end costly instrumentation. So, these could be set up in small labs across the country, but a basic understanding of the process is extremely essential. So, now after giving this part of the introduction, I will move on to the topics what we will be covering over the next 3-4 classes. That is essentially our first week. Okay. So, topics to be covered. Okay. The first one is A will be the basic concept, which partly you have started, but we will continue further. Okay. Basic concepts. The next thing what we will be dealing with will be galvanic cells. Third one we will be dealing with standard potentials. Fourth, this week we will be dealing with Nernst equation, one of the most celebrated equation. Next, we will be dealing with E0 and the equilibrium constant. We will come later about this E0 concept. Next, we will be dealing with cells as chemical probes. And we will be closing the week with biochemist use of E0 prime. There are biochemists use of E0 prime. So, a Nernst equation has been translated especially for biological application, and that is exactly where in this section what you see as the G, where we will be talking about E0 prime. We will talk about it, what are the relevance of this and hydrogen electrode and pH meter and all these things. Okay. Now, just take a little recap of where we. So, we are starting now with the basic concepts. So, part of the basic concepts we have actually started, but now we will kind of rehash where we left last week or in the last class rather. So, we talk about redox reactions, that is where we started. So, redox reactions could be classified into two groups. One is oxidation, the other one is reduction. Fine. Now, when we talk about oxidation, we are essentially talking about somebody losing electron, whereas when we talk about reduction, it is somebody gaining electron. So, in that process what happened? The electron traveled, okay, and the traveling of electron could be tapped, okay, or traveling of electron can also be considered as flow of electron, okay, flow of electron. And if we introduce another term, flow of electron or flow of charge, whatever you call that, okay, if we introduce a term to this flow of electron, rate of flow of electron, that is what we talked about, is your current. In other word, that is a quantity of charge flowing from each second through a circuit. Okay. Once again, talk about current, we are talking about quantity of charge flowing each second through a circuit. Okay. So, you see between two species, if I call this as, say for example, okay. So, if I say that this is one species of compound or something which could lose an electron, here is another compound which could gain an electron. So, if I call this as A and if I call this as B, and there is an electron transfer taking place, which is essentially a redox reaction. So, this electron transfer could be evaluated as flow of current across this species and could be tapped, as I mentioned, for energy harvesting. Okay. And similarly, this electron transfer could be tapped for sensor devices. This electron could be stored for other work, but whether the electron will flow from here to here, from A to B, is what we talked about is the function, work function of the two species. Now, having said this, whenever we talk about there is a travel of electron or movement of electron, this movement of electron indirectly tells something else. That tells this is proportional to the rate of reaction. This whole thing is proportional to the rate of reaction. So, what is the amount of reaction which is taking place? In other words, the take home message out here will be, if a reaction is taking place between this and there is a flow of electron, that indirectly signifies the rate of reaction happening. So, this part is extremely essential because we will be dealing with this in terms of the numericals as we move forward. Now, when we talk about electric charge, when we talk about this an electron moving, so it should have certain amount of charge. So, electric charge in this situation, which is represented by Q. So, it is electric charge of an electron is 1.602 into 10 to the power minus 19 coulombs, which is represented by C. Okay. Now, this is what we talk about is charge on a single electron. So, a single electron has a charge of 1.602 into 10 to the power minus 19 coulomb. Now, if we talk about a mole of electron, how much it will be charged, because you really cannot measure this charge so easily. Now, what you do is, if this is the single charge, then if you multiply it with Avogadro's number, which is 6.022 multiplied by 10 to the power 23 per mole. Okay. So, that is the value what you get is 9.649 into 10 to the power 4 coulomb, and this is what we call as Faraday's constant. So, in other words, conceptually if we talk about, that means a single electron has a charge of 1.602 into 10 to the power minus 19 coulombs. Now, you really cannot measure such a small charge on a single electron. So, the way we do it is that, so we consider how much is the charge in 1 mole. So, when you talk about 1 mole, we are talking about something in 1 mole should have Avogadro's number of particles. So, if we assume that total number of electrons in 1 mole is the Avogadro's number, which is 6.022 into 10 to the power 23 per mole. So, if we multiply that with the charge on a single electron, then the value what we get is termed as Faraday's constant. So, these are the beginning of some of the basic concepts. So, in other words, the relationship between charge and mole, if you look at it, relationship between charge and moles, we are landing with Q is equal to N dot F, where F is the Faraday's constant, N is the number of moles, Q is the charge. So, please do remember this relation. This will come very handy while we talk about the numericals. Now, from here we will talk about the two concepts. We have to relate two different concepts here. So, one concept which is emerging is your relating coulombs or charge to the quantity of reaction. This is one emerging concept. The second is relating current to the rate of reaction. So, these two concepts are exceptionally important for us to understand, because based on these two concepts we will be developing a series of numericals across it. Okay. So, let us look at it. What I said, relating coulombs, in other words charges, to the quantity of reaction. Why this is important? Because if we go back to the basic concepts where I talk about, so when we talk about, there is a reaction taking place like this. So, in other words, there are electrons which are traveling. If the electrons are traveling across it, so in that essentially means there is some form of a charge transfer which is taking place, and this charge transfer is proportional to the rate of the reaction. Okay. So, there is a charge transfer. Now, in the light of this charge transfer is directly proportional to the rate of the reaction. Now, if you look at this, essentially what you are doing, you are relating, this is where the concepts come, you are relating charge and its relation some way or other, I just put it some form of relation with the amount of reaction amount, how much reaction has taken place, because depending on how much proportionally charge has traveled. Secondly, when there is a charge traveling, as I mentioned, it is essentially we are talking about the flow of electron, flow of charges. So, the flow of charges is also an indirect measure or a direct measure rather of the rate of the reaction. So, in other words, quantity of reaction and rate of reactions, that is what I mentioned. Here what you have is the quantity of reaction could be correlated with the charge, and rate of reaction could be quantified with the current, because current is the flow of charges per unit time across a point. It could be per second. Time parameter you can resolve what time parameter you wanted to carry. So, in other words, when you are correlating something with respect to current, you are talking about the rate, right, because that is how we define current, rate of flow of electrons across a point per second, that is how we define the unit of current. So, when you talk about this much current is flowing, in other words, you are saying the rate of the reaction is proportional to this much current I am observing. Similarly, when you talk about the amount of reaction which is taking place, you can quantify it in terms of the charges. And just to close in a statement, because we will be doing bunch of problems in the next class to start off with, whenever we talk about chemical reactions, so all the chemical reaction governed by transfer of electron from one species to another. I have already talked to you about it. So, in other words, it is the potential difference across 2 points which will dictate whether the charge will travel or not. So, with this I will close in this second class with this very basic concept. So, I am going very slowly just to ensure that these basic concepts get into your mind map, and once they get into your mind map, you know exactly how to develop the story. So, let us summarize what we talked about today. We talked about whenever there is a reaction taking place, there is a transfer of electron. Rate of transfer of electron between species A to species B is in terms of rate could be defined in terms of the current, and the amount of reaction which has taken place could be governed, or the quantity of reaction could be governed by the amount of charge which has been transferred. So, the amount governing the quantity of reaction, the rate governing the rate of reaction, and this reaction will only take place when the work function of these two things are at different point. And in order from higher point to lower point, that will be a spontaneous process, but from the lower to higher point you have to use external energy. So, I will close in here, keep this in mind, and in the next class we will pick up exactly from here. Thank you.